My name is Talitha Washington. I have the pleasure of introducing our speaker this afternoon. I am here based in Atlanta. I'm a professor of mathematics at Clark Atlanta University, also director of the Atlanta University Center Data Science Initiative, and the president of the Association for Women in Mathematics. So really great to be here. Dr. Jelani Nelson was born to an Ethiopian mother and an African-American father in Los Angeles, then grew up in St. Thomas, U.S. Virgin Islands. He studied mathematics and computer science at the Massachusetts Institute of Technology and remained there to complete his doctoral studies in computer science. After his doctorate, Dr. Nelson worked as a postdoctoral scholar at the Mathematical Sciences Research Institute, now known as SLMath, in Berkeley, California, then Princeton University and the Institute for Advanced Study. He is currently a member of the Electrical Engineering and Computer Science faculty at UC Berkeley and currently serves as the chair of the Computer Science Division. He holds 2 patents related to applications of streaming algorithms to network traffic monitoring applications and was the recipient of an Office of Naval Research Young Investigator Award back in the day, and also Director of Research Early Career Award in 2016. He was awarded an Alfred P. Sloan Foundation Fellowship in 2017. His research focuses on sketching and streaming algorithms for big data and dimensionality reduction techniques for high-dimensional data. Essentially, Dr. Nelson's sketching algorithms compress big data sets into smaller components that can be stored using less memory and analyzed quickly. What probably makes him most proud? I would say probably being a dad first, and then amplifying access to computer programming and data science to youth worldwide. Today, he will talk to us about smartphone privacy, how to learn from distributed private data. Without further ado, it gives me great honor to bring forth our afternoon speaker, Dr. Jelani Nelson.
Can you all hear me well? Yeah? Good? Okay. Thank you for that introduction and for having me here. So the title mentions both privacy and learning. It'll be more about privacy. Okay. So let's get started. And this is joint work with Hilal Asi, Vitaly Feldman, and Kunal Talwar, who are at Apple, and Hui Nguyen, who is at Northeastern. So probably everyone, or almost everyone in this room, has a smartphone. And there are various features on our smartphones that we appreciate. For example, things like auto-completion, automatic spell correction. Okay. And how do these things work? Well, they use some machine learning, right? And you need data. Where does the data come from? It comes from us. So here's a little cartoon toy drawing. So you imagine their end users each has their own device. And there's data that lives locally on your device. So for example, what's the last word that you texted? And then there is the server, who in this case is, I guess Apple or whoever is providing some software service to us. And they want to understand something about our data so that they can train their models or do whatever they do to provide good services to us. So for example, they want to know here, this is just a simple example, a histogram of how many devices just texted the word X as their last word. So F is a histogram indexed by all words in the dictionary. Okay. So it sounds simple enough. I'm a device, I have my data, I just send my data to the server knows everything and then computes whatever it needs to compute. But there's a constraint, which is privacy. Do you really want whoever's providing the software service, the phone manufacturer, to read all your text messages and have all your data? Maybe not. Okay. So this talk is going to be about how to learn from your data without actually learning your data. Okay, so that is kind of slightly paradoxical, and it's going to use tools from the mathematical foundations of privacy, as you're going to see. And the basic idea is going to involve sending random messages. So here's a very toy picture. This is not real. This is not what we're going to end up doing at the end. We're not going to do anything close to this. But imagine that my text message is actually an image. And imagine that I had a baby shower. Well, don't imagine that I did, okay? And I sent pictures of myself to some of my family members of me playing one of these baby shower games, drinking from a baby bottle. So my friends will get the true message, the true image, but Apple or whoever else will get a noisified version of it, maybe even so heavily noisified that they can barely tell what's going on. But the hope is that if the image, say, goes viral and a lot of people are texting this image of me drinking from a bottle, then if they get many copies, so let's say there are 25 devices, each sending a message, and maybe a large percentage of them are sending this picture of me with a bottle, but maybe when I say large, a noticeable fraction, say at least 5% of devices are sending this viral image of me with a bottle, and some of the other ones are sending something else, then I want the service provider to know that, to learn that. Okay, they should be able to figure out, oh, this particular image is going viral. I don't know which devices actually sent it, okay, but at least I know that many are sending it, even though I don't know who exactly is sending it. Okay, so that's the kind of thing I want the server to be able to learn. Okay. So what I hope to achieve here is that each individual message looks like random garbage, thereby protecting privacy at the individual level, but the server can still learn from the aggregate. Okay. But we have to be careful because if we want to I'm a theorist. When I come up with algorithms, I like to prove that the algorithms do what I say they do. So if I say that they provide privacy, then I have to tell you what that even means. Mathematically, what does privacy mean? So for example, here's me taking that picture of me with a bottle and heavily noisifying it. And then I ran some signal processing algorithm, wavelet denoising. It doesn't matter what it is, but the point is, from the left, feeding it through the algorithm, I got the thing on the right. So this is a privacy disaster, right? Because the definition of privacy is you shouldn't be able to learn anything from individuals, only from the aggregate. But here I am learning quite a lot from an individual message, right? So that shouldn't happen. So we need to make sure that we have, solid mathematical definitions and then prove theorems about our algorithms so that we have real guarantees. We're going to use a notion called local differential privacy. The idea is going to be, as I said before, that each device will send a random message, m sub I, that's only weakly correlated with its data. Its data is x sub I. And each individual message, m sub I, should look like random noise, but you should be able to extract from the aggregate. And specifically, the definition we use, this differential privacy, is kind of the gold standard definition from back in 2006 by Dwork, McSherry, Nassim, and Smith. And what it says is, for each device, and for each possible message that could be sent M, so M is in any element in the universe of messages that could possibly be sent. And for all different data elements that the device could have, so X could be the picture of me with a bottle, and X prime could be the picture of a cat, so two totally different data elements. If you look at the ratio of the probability, the conditional probability that the device sends a particular message given that it has the bottle photo versus the probability that it sends that message given that it has a picture of a cat, the ratio of those probabilities should be bounded by something, e to the epsilon. Epsilon is called the privacy loss. Why? Because if epsilon is 0, you lose no privacy. Epsilon equals 0 is perfectly private. Why? Because it says the ratio is at most e to the 0, which is 1. The ratio is at most 1, but I can change who I call x and who I call x prime. So the inverse ratio is also at most 1. So it's equal to 1. What does that mean? It means the probability distribution of my messages doesn't depend on my data at all. So if it doesn't depend on my data, then how could it reveal anything about my data? Therefore, epsilon equals 0 means it's perfectly private. It doesn't reveal anything about my data. Okay? Meanwhile, epsilon equals infinity means the ratio could be arbitrarily large. So I could just send my raw data, for example. And of course, there's no privacy if I'm sending my raw data. Intuitively, it makes sense to say that's not private. Okay. Good. So this is the definition we're going to be using. Right? So the name of the game is to design schemes that solve various problems by sending messages from devices in a way that satisfies some prescribed privacy guarantee. Two regimes to keep in mind are small epsilon, meaning like epsilon is 0.001 or something like that, in which case e to the epsilon is roughly 1 plus epsilon, or large epsilon. When I say large, I just mean like a smallish constant like 5 or 8, something like that, but not much less than 1, bigger than 1. And large epsilon is usually what's deployed in practice, and you could say, well, privacy, I mean, the smaller the epsilon, the better privacy it is. So why would people deploy larger epsilon? And the reason is because they want utility, right? So at the end of the day, the server is trying to provide some service to us. They're trying to learn our data as best as possible because they want to provide higher quality autocomplete or automatic spell correction or whatever it is they want to learn from our data. So utility is some measure of the quality of the knowledge the server extracts from our data. And the privacy is this epsilon, that's the privacy loss. And there's a fundamental trade-off between them. As we already pointed out, if epsilon is 0, I'm sending random noise that has nothing to do with my data. That's perfect privacy, there's no utility. The server learned nothing about my data, there's no utility. The opposite is epsilon equals infinity, that's perfect utility, I can send my raw data, they learn everything. So the fundamental trade-off, so if I'm a server trying to provide good service, I'm trying to give you good utility, but there's a trade-off between that and privacy. And unfortunately, for many problems that people care about, you can prove that if you want to have reasonable utility, you just can't have fantastic privacy. There is a silver lining. The silver lining is that if you have a protocol for any problem that gives you like medium epsilon, like 5 or 8, some smallish constant that's bigger than 1, there's something you can do called shuffling, which automatically improves privacy when you have a lot of devices. It can bring the epsilon basically down to 0.01 automatically, okay? And I don't want to talk about exactly what that is, but I put some references. You can ask me later if you want to know. So for this talk, we're going to focus on developing, locally differentially private protocols for various problems where epsilon is medium, like 5 or 8 or something like that. Okay, so before going further, our first problem, I'm going to talk about 2 problems today, is going to be the one that I mentioned, which is histogram estimation. So imagine that devices hold data from a discrete universe of size k, and what the server wants to learn is this histogram of, for each x, how many devices have their data equal to x? Okay, the last word texted on the device was x, for example. And our utility notion is going to be related to mean squared error. So there's the true histogram f. After receiving messages and running some algorithm, the server is going to learn some f tilde, and I'm going to look at f minus f tilde, the average square difference between fx and f tilde x. And the whole protocol is randomized, right? Because the messages are randomized coming from the devices. So I'm going to look at the expectation of this. So what are the things we want to optimize? So there are things we care about like privacy loss, utility loss, which is this mean squared error, communication, how many bits am I sending from from the device to the server? The server runtime, I receive all these messages from these devices, I have to run an algorithm on them, how fast or slow is that algorithm? And also device runtime, I'm a device with data, I have to conditionally sample based on my data, how long does that sampling take? And kind of for all of these, if you fix 4 and look at the 5th, then the smaller the better. The smaller the privacy loss, the better. The smaller the server runtime, the better, and so forth, right? So we want to understand trade-offs between all 5 of these things, or hope maybe there is, maybe for some of them we can get them to be great at this simultaneously without having to trade things off, but we need to understand this. So we did develop some new algorithms. Before I tell you the new stuff, let me tell you kind of stuff that's classical and out there. So an old algorithm is called randomized response. So what do the devices do? Each device sends its true item x with some probability e to the epsilon p. Otherwise, it sends a uniformly random other item such that each other item is sent with probability p. This is differentially private by construction because the ratios are always at most e to the epsilon. What is p? There's only one value of p for which this makes any sense because the probability that I send something is 1, right? What is the probability that I send something? Well, I either send my true item, which happens with probability e to the epsilon p, or I send another item with probability p, but there are k minus 1 other items. So you solve for p, and now you know what p is. What does the server do then? So now we've told you how the devices behave. How does the server reconstruct f based on the messages? So for any x in the domain, how does it estimate the count, how many devices hold x? So here's what we're going to do in randomized response. So I receive these messages, m1 up to mn, one from each device. For each message m sub I that I receive, if that m sub I equals x, I'll add alpha plus beta to a counter. Otherwise, if it does not equal x, I'll only add beta. Okay? And I'm going to, this is a reasonable thing to do. I'm just going to make this be an unbiased linear estimator. Meaning, if xi actually equals x, I want the expected contribution to the counter to be 1. If xi is not equal to x, I want the expected contribution to be 0. Right? That way, the estimate is at least correct in expectation. But what are the expectations? Well, I always add the beta. And if xi equals x, I add the alpha with probability e to the epsilon p. If it's not equal to x, I add with probability p. I want the first thing to equal 1. I want the second thing to equal 0. I solve for alpha and beta, and that tells me what alpha and beta are. So now the protocol is fully specified. I've told you exactly how the devices behave. I've told you what the server does to reconstruct estimates. How good is it? I'm not going to do the math and calculate in front of you, but the communication, I would call this good communication. Why? There's basically no communication overhead. To send my raw data as an element in a domain of size k, it would take log base 2 of k bits. I'm still sending an element in a domain of size k. It takes log base 2 of k bits. There's no overhead at all. And it's very fast for both the server and the devices, right? It's like linear time for the server, and it's constant time for the devices. Okay, I guess, unfortunately, let me see what's going on. Ah, there we go. The con is that the utility loss is terrible. If you actually analyze the mean squared error of this thing, it's not good. Okay, and I'll have a plot later where you see just how not good it is, but it's really, really not good. Okay, good. So that's one example. Let me give you one more example before I get to the new stuff, which is called subset selection. That's due to Ying-Barg in 2017. Now, I fix a parameter d. D is a positive integer. I fix it ahead of time. Each device will send a random subset of the domain of size d. What's the probability distribution over subsets of size d? Well, for any subset S that contains x, x is my element. If it contains x, I send it with probability e to the epsilon p. If it doesn't contain x, I send it with probability p. Again, there's only one value of p where this makes sense, because I can say, again, the probability that I send something is 1. What does the device do? I mean, the server, what does the server do? Something similar. I want to have some linear unbiased estimator. If the messages now are sets. If the message contains x, I add alpha plus beta. If it doesn't contain x, I only add the beta. I can write down expressions for what is the expected contribution if xi equals x versus if it doesn't. The first one I want to be 1. The second one I want to be 0. I solve a system of 2 linear equations for alpha and beta. And it's going to give you an expression which, when you solve for alpha and beta, it's going to give you an expression that depends on d, right? And also p depends on d. So now d is a free parameter. You can choose d however you want. So once I have those expressions, let me calculate the mean squared error. It'll be some function of d. And then let me choose d to minimize the mean squared error. And if you do that calculation, the d that minimizes the mean squared error is the closest integer to this expression, k over e to the epsilon plus 1. If you think of epsilon, again, as being a constant like 5, e to the 5 is about 150. So this is, k is some large domain divided by 100, 150, whatever. This is linear in k. Okay? So now what are the pros and cons? The pro is that if you insist on having a scheme that provides an unbiased estimator of f, expectation of f tilde is f, you can prove that this scheme provides the optimal trade-off between privacy loss and utility loss. Even the constant factor is optimal. It's not just big O optimal. The con is terrible communication and runtime, because with randomized response, but randomized response, by the way, is just d equals 1. Okay. Randomized response, your messages were log k bits. Now your message is k bits. You're sending a random subset of size proportional to k. Okay. So that's not great. So before I tell you something new, let me tell you a meta approach, which is due to Acharya, Sun, and Zhang. let's look at the design space of all protocols we could think of that kind of look like this. So in randomized response, the messages were elements of a domain, a range of size k. In subset selection, they were size d, k choose d. Here, let's look at an arbitrary message space y. So messages are elements of message space. And let's look at a setup where for each element x in the domain of size k, we associate a subset of message space, which we call the preferred messages. S sub x are the preferred messages for x. And let's say that the size of S sub x is little s. Randomized response, little s was 1. And subset selection, little s was, I guess, k minus 1, choose d minus 1. And also, suppose that these preferred message sets form what's called a combinatorial design, which is if you look at two different elements of the domain, their preferred message sets always have the same intersection size. Let's call that L. So the mechanism is going to be kind of a generalization of what we saw before. Any element which is, so I have an element x, and I'm trying to decide what message to send. I'm going to send a random message from message space. What are the probabilities? If the message is not preferred, I'll assign it probability p. If it is preferred, I'll assign probability e to the epsilon p. And again, there's only one value of p where this makes sense, so that determines now what the device does. And so, just as before, how do I estimate the count of x? For every message I get, I'll always add the beta, and I only add the alpha if it's a preferred message. And again, I played similar games before as, I want the ith sum end of expectation either 1 or 0, depending on whether xi is equal to x or not. I can write down these expectations. I can solve a linear system and figure out what are the alpha and beta that make this work. Okay. Now, what's the mean squared error? Okay. I'm going to write down some equations. I just want you to look at the last thing. Okay. The point is you can write down some explicit calculation to give you exactly what the mean squared error is, and it only depends on the parameters of this combinatorial design. And the dominant term, if you trust me for a moment, the dominant term is the blue one. So n is the number of devices, L is the intersection size, S is the size of each preferred message list, Y is the message space, so that's the size of the message space. So basically, those parameters of your protocol are the things that determine how good your mean squared error is. Okay. So you could try to go back. Now that you wrote this down, you could try to go back and look at subset selection and try to understand why was subset selection so good? What was the L over S ratio for subset selection? What was the Y over S ratio that made everything so good? Okay. And you'll get some understanding from that. Another thing that I want is, okay, so basically the mean squared error increases as a function of both of those ratios, L over S and Y over S, so you want these small. There's another thing you want small, right? You want the communication to be small. If I want the communication to be small, what is that related to? Maybe someone can shout it out to see if people are following me. Yeah, the size of y, because the communication is log base 2 of the size of y, right? It's an element of y. So you want these things small, you also want y to be small, or log of y to be small. So good, so now and you also want a fast algorithm, right? You want to be able to basically calculate all of these server estimates. You want it for all x, right? You want f tilde. So you want all of these f tilde x's for all x. You want a fast algorithm that gives you all of them. Okay. So good. So now you're thinking about this combinatorial design question, and you're not sure what to do, right? So you look at various combinatorial designs that are out there. Maybe at some point, if you're religious, you pray. I don't know. Okay, so you think about, what does your religion tell you? And you realize, actually, it's telling you something. Okay. So, most of us, I learned about Renaissance art when I was in high school. I never really appreciated, why it was so interesting. But there's a lot of geometry in Renaissance art. In particular, there's this idea of perspective drawing where, how do you draw a 3D world on a 2D canvas to really make it look 3D, right? And there's this, idea of I have a vantage point, and Parallel lines should all intersect at the vantage point and so forth, right? So if you look at the ceiling there, this is what is this? Da Vinci, right? Last Supper, yes. So if you look, all those lines on the ceiling are parallel in the real world, but on the canvas, they're not. They intersect at the vantage point, which I've highlighted there. So you realize, this whole, Da Vinci was trying to tell us something through, Noga alone also helped out to help us realize this, that you should use projective geometry, okay? So based on the Last Supper drawing, painting, the idea is you're going to do the following thing. You're going to pick a prime q and define message space as being fq to the t. And you're going to pick t large enough so that the size of message space is at least k. So basically, t is the ceiling of log base q of k. That way, q to the t is at least k. And you're going to view every element in your domain as an element of fq to the t. Okay. And you're going to define your preferred message list to be the t minus 1 dimensional subspace orthogonal to x. So why is this good? Then, so what does it mean? It means that S sub x is all u such that u dot x is 0 mod q. S sub y is all u such that u dot y is 0 mod q, right? So you have these two linear constraints. So if you look at their intersections, it's a t minus 2 dimensional subspace. Therefore, S is q to the t minus 1, L is q to the t minus 2. You have your ratios. You choose q to be something close to e to the epsilon, and voila, like everything is good. Okay. Except everything is not good, because what if y is a multiple of x, for example? Then S sub x and S sub y are actually the same subspace, and their intersection is not a t minus 2 dimensional subspace. It's a t minus 1 dimensional subspace. So you don't get this combinatorial design property. The intersection sizes are not always q to the t minus 2. So that's where projective geometry fits in. And if you're unfamiliar with projective geometry, basically, all you need to know for this talk is, a point in projective space is a line through the origin. And, the entire line is all the same point. So we can canonicalize and say, which point is going to represent the line. If you scan the point from left to right, the first non-zero you encounter should be a 1, let's say. You normalize it so it's a 1. So good. So that's now the domain we're going to work with. So we're going to look at the domain being projective points in fq to the t. These are the non-zero vectors in fq to the t whose first non-zero you encounter from a left to right scan has to be a 1. These are the canonical points. The number of projective points is not hard to count. I'll just assert it's q to the t minus 1 over q minus 1. And I'll pick t so that that expression is at least k. That way I can identify the domain with projective geometry. Every element of the domain I can view as being some different projective point in fq to the t. And I'll define the preferred messages as being the projective subspace orthogonal to x. That is all projective points u, such that x dot u is 0 mod q. And now I don't run into this issue anymore where two different preferred message lists could intersect and keep the same high dimension. Okay, I will reduce the dimension. And I will get my nice S and L, and I live happily ever after. Okay, so this just works. That's it. This is the whole scheme. Okay. I don't know how well. Can you read this, actually? I know the font might be a little small. So let me just tell you. Okay, so basically what this table says is the new scheme is awesome. Okay, so if you look at there are 3 columns here. There's the fourth, which is the name of the algorithm. But then there are 3 other columns, which is the communication, the mean squared error, which is the utility loss, and the server runtime. Randomized response had great communication. You just send an element of the domain, log base 2 of k bits. Projective geometry response can also get you log base 2 of k bits, unlike subset selection, which is like k bits. Utility loss, we get the same exact utility loss as the optimal subset selection, which is some expression, 4n e to the epsilon over roughly e to the 2 epsilon. And the server runtime is almost linear. It's n plus k log k, but the k log k is multiplied by an e to the epsilon. So if the punchline is if you compare this to previous work, the ones I showed you, randomized response, awesome communication and runtime, terrible utility loss. Subset selection, awesome utility loss, awful server runtime and communication. There were some other works that happened before ours as well, which I haven't talked about. Maybe the most notable are Hadamard response and recursive Hadamard response. They have great communication, great server runtime. They lose constant factors in their utility loss. So their mean squared error is correct up to big O, but they lose factors of 2 or 9, okay? And I think, I'm a theoretical computer scientist. My community has a bad reputation where we're known for hiding constant factors in big O's in all our papers, and maybe even hiding polylogarithmic factors in big O tildes in our papers. So you could ask Jelani, now, why do you now care about a constant factor of 2 or 9? And the reason is, if you talk to a theoretical computer scientist and ask them why do you always hide these constant factors in your algorithm runtimes, you'll hear various answers like, well, those constant factors in your runtime depend on hardware, for example, and other, maybe what programming language you use and so forth. And our hardware is always getting better and better, so like this is not accurate. Okay, so maybe it's okay. We'll just like if we want to improve runtime by a factor of 2, we'll just wait until we have better hardware. That answer and other answers you often hear don't fly in this scenario because utility loss is not runtime. It's a law of nature. It's like the quality of the data extraction you're getting from your user devices, right? There's no, I guess you could say, well, I could improve the quality of my data extraction if I had more users. That's true, but you have to sell twice as many iPhones or something. And maybe that's, you'd love to do that, of course, but it's not as under your control, okay? Right. So yeah, you would never, for example, like in the machine learning community, if you look at, generalization error, you would never say, oh, I only lost a factor of 2 in my error rate or something, right? People try to squeeze every last bit out of that. So, okay. So maybe I'll just do some plots. What you're seeing looks, for example, on the bottom 2 plots are the following. So we implemented basically all the algorithms I showed you in the table. Our new algorithm is PG, projective geometry, in teal. Subset selection is an optimal algorithm in terms of mean squared error. That's in dark blue. And what's plotted here is an empirical CDF of the mean squared error. So we made up some fake, database. The algorithm is randomized, so we ran it 1,000 times. And each time we ran it, we tried to reconstruct an approximate histogram and see what is the actual L2 error. And then this is the empirical CDF of the L2 of the mean squared error, right? So you can see that our curve, the PG curve, and the SS curve are essentially on top of each other, because that is the optimal curve, right? Whereas even things that, in theory were off by constant factors, like Hadamard response, which is green, or recursive Hadamard response, that's RHR, which is red, they really are off by constant factors, even empirically. Okay. We also looked at runtime. So the previous state-of-the-art algorithm in terms of optimal mean squared error, on about 3 million, a domain size of 3 million with epsilon being 5, took about half an hour to run on my desktop to reconstruct F, to approximately reconstruct F. Projective geometry response took 37 seconds. Hadamard response and recursive Hadamard response each took like between half a second and a second roughly, so they are faster. They're faster, but they lose constant factors in your mean squared error. We also have a hybrid algorithm we call hybrid projective geometry response, which lets you basically trade off runtime for mean squared error. So, it gets you better mean squared error than RHR and HR, but worse than PG. Okay, it's actually the yellow curve between the red and the blue. But it's faster. It's faster than projective geometry response. Okay, making our scheme fast. So I told you what our scheme is. Why does it lend itself to a fast algorithm? Okay, and the idea is to basically do dynamic programming. So, when I was an undergrad, I was very into programming competitions like Top Coder. Nowadays, the new generation plays Code Forces, I hear, or Leak Code and HackerRank. But I used to do Top Coder when I was younger, like 20 years ago. And I had to implement a lot of dynamic programming things for contests, but this is the first time I ever used DP in like real life. Okay, so why does dynamic programming fit into this? And I know we're coming from lots of different communities here. So my fellow computer scientists in the crowd probably talk about dynamic programming all the time. I'm just curious, who here has no idea what I'm talking about when I say dynamic programming? Okay, but most people do. Okay, so a couple didn't. So okay, let's just say recursion. Okay, recursion with some speed up using by memoizing things in a table. But you'll see what I mean. So if you remember, this is what the reconstruction algorithm looked like, right? So I'm trying to estimate how many devices had X as their data. For each user's message, I always add the beta, and I only add the alpha if they sent a preferred message. So I can factor out the alpha. I can say, well, everyone adds beta, so I get a beta n. And then for the other part of the sum, I factor out the alpha, and I have to calculate basically I have to just count how many messages I got were preferred for X. What does it mean to be preferred? To be preferred, it means that x.u is 0 mod q. So let me now define a new histogram y, where y sub u is the number of copies of u I got as a message. So that sum, the number of preferred messages I got, is I sum up over all u that are orthogonal to x of y sub u. How many copies of u did I get? That's exactly the same thing as the top sum. So I need to be able to calculate that sum for all x simultaneously to be able to reconstruct f tilde. For each x, naively computing that sum would take about k over q time. That's how many summands there are. There are k possible values of x. So naively computing this would take k squared over q time, quadratic time, not linear time. So I'm not happy with this. So I need to be more clever. And this is where the dynamic programming comes in. So I need to come up with some recursion. So what I'm going to do is ignore the text and just look at the equation in the middle. I'm going to define a function, capital F(a)(b)(z), which is the sum over all u such that the length, remember now, u is a t-dimensional vector in FQ. It's a t-dimensional vector in FQ. I'm going to look at all u such that the length j prefix of u is a, okay? And the length t minus j suffix of u dotted with b is z mod q of y sub u. Now, under this definition of capital F, f tilde x is just alpha dot f times the empty vector, the vector of length 0. I'm going to let a be the empty vector, x 0, plus beta n. And the nice thing about defining capital F this way is it satisfies a recurrence relation. So I can use recursion with a lookup table. Recursion with a lookup table is basically dynamic programming. Okay, and there's the recurrence. I'm just writing it to show you there is one, but we don't have time to really think about it. But it's really at the level where if you're teaching an undergraduate algorithms course and you're teaching dynamic programming, this is doable. Solving this, just telling them like, how do I actually compute these f tildes is an undergraduate algorithms exercise, okay? I promise you. And it's implementable. In fact, I coded it up, okay? As I mentioned, it's possible to trade off utility and time. Let me not talk about that because we're low on time. And let me just say, in the last few minutes before we open up for questions, one more problem that LDP comes in with something interesting is high dimensional mean estimation, which is also relevant from learning from device data. In some hot field that people call federated learning. So the idea in federated learning is, again, you have a server and you have a bunch of devices, and each device has their local data. And now you want to train an ML model. So the ML model has some parameter, theta, which is some d-dimensional vector, like all the weights in a neural network or something. And you want to minimize some loss function, which is a function of theta. And you're going to do that with some distributed optimization algorithm. Right? So that's what people call federated learning. The idea of federated learning is that the data stays on the device, right? And the devices are participating in the running of the learning algorithm. You don't just send your data to the server and the server runs the algorithm. Okay, and you want to do this privately. So for example, if each device just sends its gradients, based on its local data to the server, well, that gradient is a function of your data, so it reveals information about your data. So you want to send some noisified gradient, right? And then the server might aggregate the gradients by averaging them, which is exactly what I said, mean estimation. So that's why we look at something like high-dimensional mean estimation. You should think of some distributed optimization algorithm, but we want to do it privately. We can't send raw gradients because that would reveal stuff about our data. Okay. Let me actually skip some of this. The second problem for today is just that. Every device is holding some d-dimensional vector, which you should think of as a gradient that was locally computed. And the server wants to compute, say, the average of the gradients. And you want to compute a mean which is close to the true mean, let's say, again, mean squared error, expectation of L2 norm squared between the true mean and the computed mean. So what's out there? There's an algorithm of Ducci, Jordan, Wainwright. I don't know if it has a name in their paper. I don't think they named it. And there's another one by Bomek et al. That they called PrivUnit. And the expected mean squared error is this dimension over number of devices times the min of epsilon and epsilon squared, which is asymptotically optimal. In fact, PrivUnit is not only asymptotically optimal, but it is the optimal algorithm. That was shown later by Hilal, Feldman, and Talwar. If you insist on a mechanism that produces an unbiased estimator of mu, they can show that this particular algorithm, PrivUnit, actually gives you the best possible mean squared error. Not even the best constant, it's like greater, it's like less than or equal to. The mean squared error of PrivUnit is less than or equal to that of any other mechanism, period, which is unbiased. And it's actually some kind of continuous generalization of randomized response. So let's say, for example, that the vectors that you're computing the mean of live on the sphere. You pick a spherical cap of a certain size around your x, and with some probability, you send a random element of the cap that you're in, and with the remaining probability, you send a random other element in the sphere that's not in your cap. Kind of like randomized response. You either send your true vector, or you send another random element of the domain. It's like here you send a random thing in your cap or something that's not in your cap. And you have to you have to choose the right sizes of the caps and stuff to get the optimal thing. I'm running very low on time now, so all I'll say, maybe one more minute, then we'll take questions, is this PrivUnit thing, basically, there's a way to implement it with D communication, where D is the dimension, and have time D. Or you can get communication which is much less than D, like log D, but then the runtime becomes D times e to the epsilon. So there seemed to be some kind of trade-off, again, between communication and runtime on the device side. And I guess what we showed is that okay, so I unfortunately don't have time to show you the details, but we showed that this trade-off is not inherent. You can actually get optimal utility loss and really fast device time simultaneously. And the key ingredient was random projections in the Johnson-Lillenstrauss lemma. But if you have questions about that, maybe come see me or look at the paper. It was with Hilal Asi, Vitaly Feldman, Kunal Talwar, and Huiguin. So at that, I guess now we have a few minutes left, and I'd be happy to take questions.
I had a quick question about the notion of optimality. So I think you said you literally get the optimal leading constant of 4. You can't even do better if you allow for more communication. But is this is it optimal in a worst case sense? Like what if my histogram is very sparse, say? It has a small number of very heavy elements. Is this the end of the story, or is it possible you can do even better?
If you know more information about the histogram can't be an arbitrary histogram, but
yeah, like for words or bigrams, you might imagine it's like very spiky histogram.
Yeah, I don't. Okay, good. I don't have a good answer. I don't know the answer to that. Whether you can use such information about the histogram to do better than like a worst case histogram. I'm not sure what the answer is.
Okay, cool. Thank you.
Yeah.
Okay, thanks for a nice talk. So in this randomized message setting, if I'm not misunderstanding, like even though you might, in the general case, not be able to reconstruct the individual message,
Yeah.
if you're not careful what distribution you're sending randomized samples from, it could be possible to sort of discern between when a sample is randomized and when it's a true message that is being sent. So is that a problem that sort of conditioned on true messages being sent, you can actually reconstruct the individual messages? And is that a problem for other methods than
No,
randomized messages?
So I mean, so so I guess you said like, often you see garbage, but sometimes you'll see something that's not garbage, right? Like you'll see a picture of a cat and you'll be like, oh, this must have been the true message, so therefore I learned something. So that's not really a concern, and the reason it's not a concern is, if you really look at the definition, like if my true picture was me drinking from a baby bottle, like there is some chance that the protocol, like in randomized response, for example, there is some chance that the protocol will send a picture of a cat, and vice versa. So, I mean, randomized response is a really terrible algorithm for large domains in terms of utility loss, because the probability that you send the true image is like 1 in the size of the, it's almost 1 in the size of the domain, right? But what is the size of the domain? It's the size of all images. I mean, it's huge.
But I guess what I'm trying to say somehow,
Yeah.
if you were not very careful with the randomized messaging, and you said that every 100 messages is going to be the true message, and every 99 messages is going to be like random normal noise,
Yeah.
then I could absolutely discern when the message is true, because it's just like either it's complete noise or it's a true message. So then sort of every 100 message, the privacy is sort of gone, right?
Right.
So how do you make sure that you sample from a reasonable?
No, but so in randomized response, I mean, first of all, at the end of the day, we're not using randomized response. But if it were randomized response, the probability that I send my true message is 1 in the domain size, right? So it's not exactly 1 in the domain size, but it's close to that. So the point is, when I do see something that doesn't look like garbage, it's equally likely to be any non-garbage element of the domain, right? So, like, I don't know. Like I could see the true image, or I could see an image of this room, or I could see an image of a bird flying in the sky. All of those are almost equally likely, right? So I don't know like that what I got is actually revealing anything. I don't know if that addresses your question.
I'll ask later.
Oh,
But
okay,
thanks.
okay.
Thanks.
Okay.
Great. Thank you for the great talk. If you view the histograms as maybe unnormalized probability distributions, it would be also reasonable to think about learning them in L1 rather than in L2. So do you know optimal algorithms for the LP versions of this problem?
Yeah, I know people have definitely looked at other measures of error, not L2, but like L1 as well as L infinity. So this CKO paper, Chen, Kairuz, and I forgot, Ozgur maybe. I don't remember whether there were matching lower bounds though, but there are algorithms, there are upper bounds that people have looked at.
All right, cool. Thanks a lot.
Okay, last question, yes.
Thanks for the talk, cool stuff. So in the first problem you were looking at, you talked about that sort of the meta algorithm with this trade-off between essentially communication utility, and we're able to get a little bit of a best of all worlds, but and like optimality, but in a broader like information theoretic sense, do we have any way to like characterize the information theoretic best possible trade-off between communication utility, let's say across all possible DP algorithms or something like this?
Okay, so the question was, could we prove trade-off lower bounds between these various quantities, right?
Yeah, pretty much.
But I think part of the message that we wanted to convey was that essentially there is no trade-off, right? Because the optimal communication is sealing log base 2 of k bits, and the optimal mean square error is 4n, e to the epsilon divided by e to the epsilon minus 1 squared.
And that's optimal across all algorithms?
Yeah, like even if you ignore the other parameters, like if you just want to minimize that quantity, like that's the best you can do.
Not even ignoring the meta algorithm, that's the best
Right,
you can do?
yes.
Okay.
And we get both simultaneously, right? But then our runtime is not n plus k, which is randomized response. Our runtime is n plus k log k e to the epsilon. So there's still potentially room to improve the runtime, but then, you're not going to be able to prove lower bounds there using information theory. Like humanity doesn't know how to prove runtime lower bounds on anything, basically. So.
All right, cool. Thank you.
Okay.